Okay, so welcome to lecture 20. This is going to be on biasing. Just before we start, some announcements. Homework number 7 is online and it's going to be due on Friday via Gradescope. The pre-lab to lab number 3, that's due this week. I guess some of you have it due today. The experimental part of lab number 3 is due next week. And the lab number 4 pre-lab is already online. That'll also be due next week as well, but since you cannot access the needed instrumentation, you actually won't do the experimental part. So you need only do the pre-lab part of that lab. And so I guess, let me fix what I said. That then doesn't need to be due next week. It could be due the week after, actually, since you're not doing the lab anyway for that. So that lab requires the 4145 semiconductor parameter analyzers, and those are big pieces of equipment that sit in the lab that you'd be able to access if this were an in-person class, but right now it's just not possible. So instead of actually measuring some of the things you'll measure, you'll at least calculate some of those things as you usually do in pre-labs. So any questions about logistics in this class? I guess we're honing in on a midterm that will come at the end of the month, and when we get closer to that, I will start talking about some of the details of how we do that. I guess that's all I'll say at this point. All right, so seeing no questions about any logistics, let's look at the lecture topics. So last time we applied a large signal BJT models and considered regions of operation in a DC circuit, and several DC circuits actually. Today what we'll be doing is heading back to some physics and sort of look at output resistance. So that's going to force us to go back and look at some bipolar junction IV characteristics. We'll then move into an important topic, which is parameter independent biasing for discrete BJT. So we looked at a few DC biasing circuit examples last time. Now we're going to really look and see how to properly design the biasing for a BJT, and then if we get to it, we'll talk about discrete MOS biasing. Okay, so moving right along, let's take a look at some of these BJT IV characteristics. And so some of these we've already looked at. And so when you look at a bipolar junction transistor, often you care a lot about the VBE voltage, which is the voltage applied between the base and the emitter. But also people like to think of the VCE voltage, the voltage applied between the collector and the emitter. And a lot of times the reason why you're interested in this is because the resistance that you see between the collector and the emitter becomes an important thing in certain transistor circuits. So if I went and took a closer look at this, then basically I would be able to identify that if I look this way and I'm looking at the resistance there, then that resistance I'm often going to call R0, which is going to be a small signal resistance. And that actually is going to be equal to the small signal quotient between VCE and IC. Okay, I guess if I really want to make this, if I want to make this small signal, I'll do it this way. You don't know what small signal is yet, so I'm just saying it right now. You kind of know what small signal is because we talked about it when we talked about the resistance across an MOS transistor. And I'm using that term again, that SS stands for small signal, but I'm not going to say much about it yet because we're going to have many lectures about that later on. But looking at these characteristics, one characteristic you can plot is this collector current IC versus the VBE voltage. And so you already know that this looks like a diode, because that's what the base emitter junction is. And so it's going to have a characteristic that looks just like a diode here. And so it goes up very quickly. And because it goes up very quickly, we were able to say that for any given current that we have flowing through this device, it's pretty much the same VBEs that was right around 0.7 volts. The other curve that we're interested in is a curve of the collector current, so the current going through the device, versus VCE. And again, we're interested in that because that determines the output resistance of our device later on. And if you plot that, and you plot that versus different values of base current, then you see a curve that looks a lot like the MOS curves that we have. Okay, so it goes up and then stops. It has a sort of a linear region here, and then it goes up and then it stops and then goes straight here. And if it were ideal, it would go flat but something is not allowing it to go flat, just like something didn't allow MOS transistors to go flat here. And that's really what generates your resistance. So if I said that R naught was equal to VCE divided by IC, well, if this is IC and that's VCE, then the slope right here, that I guess I'm pointing out right here, that goes as 1 over VA. That's going to be related to the output resistance. So I'll just say right now, that'll be related to output resistance. And we'll see that later on. But right now, what we want to do is just take a look at these curves here and understand that this is a lot like the MOS curves, except as confusing as it might be, this region for MOS is called the saturated region. That's where we like to operate. This region for bipolar is the forward active region. Again, that's where we like to operate. And you'll see why when we start talking about amplifiers. This region here, very unfortunately, is called the saturation region for bipolar junction transistors. This is history. We cannot change history. I can't let you out there in industry with a different name for this here. So you're going to have to call this region the saturation region. For the MOS transistor, remember this region was called the linear region. And for MOS, you want to operate in saturation because it's out here. For bipolar, you want to avoid saturation if you're making an amplifier. So that's kind of unfortunate, but I guess moving right along here. Looking at this curve in more detail, the way that we model the amount of slope that we have here. Remember in MOS, we modeled it by a lambda parameter that was multiplying VDS. Well, in this case, we're doing the same thing. We're taking the initial collector current, which was given by this equation for bipolar. It's an exponential of the VBE voltage. And we're multiplying that by a 1 plus VCE divided by V sub A. And so V sub A you can think of, 1 over V sub A you can think of being the same as lambda in the MOS world, except in the bipolar world, when they were first deriving the theory for this, what they did was they took these curves, they extrapolated back, and these curves would extrapolate back to the same voltage back here, which they call the early voltage V sub A. And so they use that voltage there to determine the equation. Well, in the equation, that then governs the slope of all of these lines here. And so the question is, why use VCE in this case? I just told you why. It's because of the output resistance. We're going to be interested in that very much later on when we talk about amplifiers. But one thing you should recognize that we're using VCE, but VCE in this case is really the same thing as VCB. Because if you look at what VCE really is, VCE is equal to VCB plus VBE, right? So it's equal to the voltage drop from the collector to the base, and then also the voltage drop from the base to the emitter. You know that VBE, because it's a diode turn-on, for a given current, it pretty much stays constant. It's right about 0.7 volts. So as I change VCE, if I have a transistor that's in the forward active region, which is where this is here, and our main interest, where the slope is there, that means what we're really changing is VCB. And so we're changing the reverse bias across the base collector junction. So if I increase VCE by a certain amount, that pretty much means that VCB is going to increase by that same amount. So that's what this equation is saying right here. Okay, so why am I focusing so much on VCB? I'm focusing that because that is what happens physically for this. So let's go back and take a look at this physical model of our bipolar junction transistor. So this is an NPN transistor again, so emitter, base, collector, N plus PN type regions there. And so what is happening physically? So I assume that I'm applying a VBE that's forward biased here, to forward bias this so that we get in the forward active region. VCE, I assume, is a reverse bias voltage that I'm applying. Now, for a given VCE, I'm going to have a certain width of my collector base junction. So here's my collector base junction here. And so I can identify a width of that collector base junction right here. So let's say that that's X1. Okay? And so X1, I'll write it here. That is, I'll define as a depletion region width at the base collector junction for VCE equal to 1 VCE, which I'll call VCE1. Okay? And I guess I've gotten ahead of myself here. I have the green thing there. I won't erase that, but ignore the green part there. I'm going to use that in a second. Forgot to erase it before making this slide here. But we're only interested right now. This is the depletion region X1 that we're getting for this VCE1. And let's say for that VCE1, you know what the current flow is going to be. The current flow is going to be affected by the slope of the minority carrier distribution in my base. And so say that slope looks something like this. Say this was the injection point, and then this is going to go down to that point there. So that's going to be my minority carrier injection there. And we know that the current, so I could say J of N, which will be the drift current, is going to be proportional to the slope of this curve. Right, so I can write down number 1 here. For this particular case of VCE1, I could say that if I have VCE1, that creates a depletion region of X1, because I'm reverse biasing that collector-base junction, and that then generates a IC1, a collector current, that's going to be proportional to the slope of this line, where this is that line right there. Okay? And so now let me take a second case. Let's take a case, and here's where I come in with green. Let's take a case where I increase that voltage across the collector emitter, which means increase the voltage across the collector base. So say I increase VC so that I go from VCE1 to VCE2, where VCE1 is less than VCE2. Okay, this basically means if I do this, then that means that my collector base voltage, the reverse bias across the collector base, I've just increased. And so if I do that, now my collector base width is going to be wider, right? Because I just increased the voltage across the collector base junction. That increases the depletion width in the collector. It also increases the depletion width in the base. And so I can write up here that X2, I'll just define as the depletion region width at the base emitter junction for now VCE equal to VCE2, which is greater than, I don't have to say much greater than, but it's greater than VCE1. Okay? And so if that's greater than VCE1, then what happens is that X goes up, okay, and equals now X2, which you could see up here is a wider depletion region. So this is wider than X1. And what that does is it basically means that the slope, so I'm assuming I still get injected current up to that point, but now this minority carrier distribution goes down here. Okay, it goes down to the edge of this depletion region X2 in the base. And so what that means is that I now have a larger slope there. And so I still have the case with X2 that my IC, which I'll call IC2 for case 2, that still has to be proportional to the slope of the minority carrier distribution, which is this line right there. But you notice that that slope is larger. Because that slope is larger, this slope is greater than that slope. Okay, therefore, I can say that IC2 is greater than IC1. And that then is the reason why on the left side, as I increase VCE for any of these curves, the current does indeed increase with every slight increase in VCE. That's what causes this slope. That's what determines this early voltage, and that's what determines this equation here. Okay, so to summarize this, I just told you physically why this is happening, but now let me summarize what does happen in equation form. Because I have this, I can now write that when VCE goes up, make that look like a CE. When VCE goes up, IC goes up due to a decrease in the XBC depletion width. Okay, and so because of that, the result of this is that my collector current becomes a function of IB and VCE, not just IB. And remember, we're talking about the forward active region. So we get this in forward active, and we get that equation. IC becomes the regular IC equation that we already know that neglects this change in the depletion width, times now, to account for that change in the depletion width, VCE divided by what I just showed was the early voltage. Okay, so this comes about because you get a change in that base collector depletion width. That's physically what's causing this. And again, we're going to care a lot about this because it's going to determine the output resistance of our bipolar transistors later on. Okay, so with that, I'm going to stop talking about physics, at least for the moment. I'm going to come back to physics when we start talking about high-frequency analysis. But right now, we know enough about physics to be able to start talking about circuit design using bipolar and MOS transistors. So let's now proceed to do that. And the first thing that we need to worry about if we want to design an MOS or a bipolar transistor circuit, and in this class we'll generally be looking at amplifiers, is we have to bias these devices correctly. And so what is meant by biasing is DC biasing. We want to make sure that we can establish a certain operating point. So I defined last time what an operating point is. That's the voltages at all the nodes. That's the currents running through all the branches. Well, it turns out that operating point pretty much decides all of the characteristics of the amplifier. And so we need to know how to get that operating point correct first before even knowing how to design this amplifier. And so let's talk about biasing, first for discrete bipolar junction transistors, then for MOS transistors. So I'm talking about parameter-independent biasing. Why do I care about parameter-independent biasing? And what do I mean by parameter-independent biasing? Well, basically, like I said, the behavior of an analog circuit depends heavily on its DC operating point, or what we'll call a DC bias point. For bipolar junction transistors, the collector current is the most important. Okay, so while you're designing circuits later in this class, your main goal is to make sure that your collector current is a certain value. And so we need to establish that collector current value. But when we establish that collector current value, we need to make sure it's stable against variations in environment, in your circuit board, and all sorts of different things. And so what that means is we need to make sure it's stable against variations in some of the physical parameters we talked about. Those being beta, which is that current gain we talked about, VBE, that turn-on voltage, and I sub S, which is that saturation current. And so let's talk about these different parameters. So you saw the physical equations for these. You saw that they depend on the doping concentration of the emitter, base, and collector, the sizes of the emitter, base, collector, etc. But how about our ability to control them? And so beta is hard to control. It varies from process to process. The one thing you can be sure of with beta, most of the time, is it's going to be large. right? We know it's large, but we can't necessarily pinpoint its exact value. And that's kind of a theme in a lot of analog design. That was the same thing with the gain of an op amp. And so you're seeing somewhat where that comes from. The gain of the op amp will depend on things like beta, etc. And so that's why the gain of an op amp is not necessarily going to be very well specified, I suppose. I mean, it's dependent on beta, but not so much. I guess I should say it's dependent on R naught and some of those things even more. But beta is hard to control. I sub S, that's also hard to control. It depends on your process. It depends on all sorts of different things, doping concentrations, etc. This VBE depends on I sub S, although only to the natural log, so it doesn't depend heavily on I sub S. But it does depend on temperature, right? This KT over Q, that's VT, right? So VT is KT over Q. And so VT depends on temperature, so VBE depends on temperature quite a bit, because VT depends on temperature. Okay, and so when we make a strategy to bias up a transistor to get a certain collector current I sub C, okay, it's important that we create a circuit that suppresses the dependence on beta and IS and VBE. Right? If we can create a circuit that suppresses the dependence on them, then we can make sure that I sub C stays constant with time, with environmental changes. Say if the temperature changes, then I can sort of rest comfortably that my I sub C doesn't change, which means my amplifier doesn't change too much with those changes in temperature. Okay, so what I want to do now is talk about some biasing strategies. How can we bias up a transistor, which means establish its collector current, in such a way that it is not very dependent on beta, IS, and VBE. Okay, so let's talk about this. So I want to compose some biasing strategies. Okay, so let's try a couple things. First thing I'm going to try is just use a voltage source and a collector load. So a collector load resistor, which I'll call RC. And again, that little line through the C means it's a capital C. And I guess you don't understand yet why I'm being so particular about that, but you will later on. Just right now, let's get used to using those capitals and that sort. And so that says I have a VCC. And so, sorry, to bias this up, I'm going to put a VCC up on for the circuit. This is the battery that I'm using, my power supply. And I'm going to send this VCC through that collector resistor, which I'm calling RC. And I have my transistor down here, right below that. And I'll let my emitter go to ground. And I'm just going to put a voltage source, VBB, at the input. That will set the voltage at the base. And so, again, I want this I sub C. I want to set that I sub C to a very specific value. So when I draw something like this, I said this last time, but I could say it again just to make sure that it got through. But here's my circuit again. Basically, the total circuit that I'm drawing is this. So I'm putting the same battery here. That was VBB. And I think I want to move this, give myself a little more space there. And that VCC is actually another voltage source is what I'm drawing. And all of those then go to the same common ground that I have out here. But this voltage source is VCC. And so I'm just showing the equivalence between what I drew on the left and what I drew on the right. And I'll just emphasize that we will be drawing everything like what's on the left from now on in this class. We're not going to draw the details of the batteries and that sort of thing because it saves us time. And so in this circuit, we could start analyzing this fairly quickly, so that this collector current right here, immediately I can write the equation for that. We know the physical equation, that I sub c is going to be Is times E to the VBE over VT power, which I know that VBE in this case is just VBB. So that means I can write that this is equal to I sub s times E to the VBB over VT. Okay? So what can I say about this? This is how I've just set my collector current I sub c. It's equal to this equation here, but I don't quite like this equation too much. And so here are the reasons why I'm going to complain about this. If I want this to be stable with respect to different things, process variations or temperature and that sort, then I have this directly dependent on I sub s. Okay, so this I sub c, it varies directly with this I sub s. I just said I sub s may not be the most predictable thing because of process variation, so I don't like that. I'm going to put a big X there. Okay, this current also is exponential with that thermal voltage Vt. Remember that thermal voltage depends on temperature. That's Kt over Q. Okay, and so I don't like that because that's too dependent on temperature. Okay, the other thing that I'm looking at here is because of this exponential dependence, this VBB here, this must be very precisely set. That might not be easy to do in a circuit. So I have to set that to many significant figures there. Maybe 3 or 4 significant figures, maybe 5 to get the current that I want. And so I don't like that either. Okay? And so, in essence, to summarize all these complaints that I have here, strong dependence, right? This circuit has a strong dependence on I sub s and Vt. Okay, and that strong dependence, that's not good. I don't like that at all. Okay, plus, as I've said, we don't normally have a VBB in integrated circuits. Let me write that out, integrated circuits. Abbreviation ICs, right? So we just have VCC in general. Okay, so this circuit here, it's got a VCC, but I had to add a VBB. And the VBB I had to add had to be very, very accurate. And that's not a good thing. Okay, so how can I relax some of the need for extreme accuracy here? And one thing I could do is just alter this a bit to put a base resistor to VCC. So this VBB I don't like here. So what I want to do is just add a base resistor that goes straight to VCC that then establishes a different voltage here at the base, which gives me the right VBE, but also establishes the base current going into here. So let me show a second circuit as we work to a better circuit, and that is add a base resistor to VCC. Okay, so that circuit's going to look like this. I'm going to have a VCC. I'll have my collector resistor, my transistor, which will go to ground. And now here, I'm going to use a resistor RB to establish my base current, IB, into my transistor and to generate the needed VBE voltage across this to get my goal, which is a very specific RC. Okay? And so with this, I can just do some very simple circuit analysis here. I could say that IB, I know what that current's going to be because I know that this VBE is going to be a VBE on across the transistor base to emitter. So I could just say IB is going to be VCC minus that VBE on voltage divided by that RB resistor. Okay, and so from this, then I can say that my I sub C is just going to be equal to beta times IB, which is then going to be VCC minus that VBE on, which is 0.7 volts basically, divided by RB divided by beta. Okay? And so this does have one nice thing about it that I like. And that one nice thing is that it has less dependence on VT and IS when VCC is much greater than VBE on, which is generally the case. Okay, so this top portion of this I like, and I'll write it out, because I have less dependence on VT and I sub S when VCC is much larger than VBE on, which is about 0.7 volts, right? And so because of this, I consider this better than the circuit above. But I have a problem, and that's what I see in the denominator of this, that beta. This current is heavily dependent on beta. That's not good. Because remember, beta is one of these things that can change quite a bit with our process technology. Okay, so how do I reduce that dependence on beta? And so let's try another circuit to try to reduce that dependence on beta. And so this will be attempt 3. Let's add an emitter resistor. So let's keep our base resistor. So I have a base resistor to VCC, which I liked because it took away the need for a VBB and it reduced the dependence on VT and IS. But then add to this an emitter resistor. Okay, so let's take a look at this circuit. So I'm going to have a VCC here. I will have a collector resistor, RC, that's feeding into my transistor. And now I'm going to load this with an emitter resistor, RE. And I'm still going to have that base resistor coming into my base. So there's my RB. And that's going to determine my IB based on what VBE I have across the device, which is basically going to be VBE on. And there's the IC that I'm looking for, but on the way to it, I might want to determine the IE that I have. And so in this case now, to analyze this circuit, you do the same thing that you've always done, that we just did before, and that's apply KVL in this case. So if I apply KVL around this, where KVL is Kirchhoff's voltage law, of course, then I get VCC is going to be equal to the voltage drop across my resistor RB, IBRB, plus the voltage drop across the base emitter junction, plus now the voltage drop across the resistor RE. Right? I need to get from VCC all the way down to ground, and I have to go through all those parts to get there, so I need to add all the voltages through all of those parts there. This now, I can plug in things that I know. So I know that IB is equal to IC over beta. So I get an IC over beta times that RB. I get that VBE here. And plus, I know that IE is IC over alpha. So I'm going to multiply that by RE. And so finally, I'm going to be able to write that I sub C is going to be equal to VCC minus VBE divided by RE over alpha plus RB over beta. Okay, so alpha is basically 1. I'm not that worried about alpha changing with environmental conditions or with doping concentrations. I'm worried about beta doing that. I'm also worried about VBE still. So I'm still worried about stability against beta and VBE mostly, where VBE contains the dependence on I sub S, of course. And so let's look at stability against these things. So for stability against changes in VBE, what do I need from this circuit? I need to choose VCC much greater than whatever VBE is going to be. You know VBE is going to be about 0.7 volts. So I want a VCC that's much greater than 0.7 volts there. What that will do is it will reduce all dependence on delta VBEs because VCC will dominate over that. If I want stability against changes in beta, then what do I need? So I need this term RE over alpha to dominate over this term RB over beta. So I need effectively RE over alpha to be much greater than RB over beta. Okay, so if I look at this then an example of this last one here, oops, let me change that to black. If I want RE of alpha to be much greater than RB over beta, then much greater means that I want it greater than or equal to 10 times RB over beta. Okay, that's a good choice. If you choose something like that, then your bias point will be fairly good. Okay? But there's a problem with this circuit still. And that is to get the needed IB, I need a large RB. Okay, and I don't like RB being too big. And so the solution to this that we often use is we reduce RB, or reduce the needed RB. I'm trying to erase, there it is. By reducing the voltage applied across it. And so this now leads us to finally the standard way that people will bias up a bipolar transistor circuit if it's a discrete off-chip circuit. There'll be different biasing techniques for on-chip circuits. But right now, at least, this is our standard parameter-independent biasing that you will use time and time again in this class, especially for your design labs that are coming up after Lab 4. Okay, so this is standard parameter-independent biasing. Let me write what I said before. This is for discrete bipolar junction transistor circuits as opposed to integrated circuits. For integrated circuits, we'll use things like called current sources. Well, you know what current sources are, but we'll use current sources that are going to be designed using transistors themselves. But at least for discrete circuits, which you'll be building in this class using your lab kit, this is the standard circuit that you'll be building time and time again. And so now you understand why you're doing it, because you want to make sure that this circuit is resilient against changes in transistor parameters. So it has that collector resistor, it has that emitter resistor, but now instead of just having a base resistor going straight into the base, it uses a voltage divider of resistors. And I'll call this one R1. I'll call that R2, and I could say that I have a bias current, I bias, which I'm sort of drawing through that whole thing. Maybe I shouldn't draw it through the whole thing. Usually I'll draw it through the whole thing because the base current should be much less than this current, but I'll just do this right now. That's now our I bias current running through this. And so how do we analyze this circuit? Well, a good way to look at this circuit is to just equate it by making the Thevenin equivalent of the R1, R2 voltage divider. Right? So this hopefully you can recognize as just a voltage divider. Putting my dots all over the place. I want to get that right. Okay, so I'll condense this circuit to this. So I have that RC resistor, I have VCC, there's my transistor, I have my RE, and if I just make this into a Thevenin equivalent circuit and call this VBB, then VBB is just going to be equal to VCC times that voltage divider. So R2 over R1 plus R2. This value of resistance, RB, is just going to be equal to the parallel combination of R1 and R2. And that's my base current. That's my collector current. And that would be my emitter current. And so if I do the same thing, this is the same circuit as before, right? And so all I would do is apply KVL again here. Kirchhoff's voltage law. And if I do that, I'm going to get a collector current equal to VBB minus VBE over RE over alpha plus RB over beta. So the main difference here from the previous equation is now I've stuck in VBB, and the value of this RB is a little bit smaller there. Okay, and so for this, it's the same kind of thing that I had out here. I can write out bias stability requirements for this, and I'm going to do that because I'm going to enumerate them this time for you. And so let me just write out, thus for bias stability, we want the following. 1, we want this VBB voltage, which is that voltage divider output voltage, to be much greater than VBE. Okay, we want that. Why? That's for insensitivity to VBE, which is a parameter that can change. And that contains sensitivity to IS and different physical parameters there. 2, just like before, we want RE over alpha to be much greater than RB over beta. And that's for insensitivity to beta. Okay, and as a rule of thumb, like I said before, this means you basically want RE over alpha to be greater than or equal to 10 times RB over beta. Okay, and so what does this tell you? This basically also says we want RB to be small. Okay, that means we want R1 and R2 to be small, which in turn means that that I bias current that I wrote, which we can say is the current going through R1, but it's really like the current going through R1 and R2. We want that I bias current to be large. And so a third thing that I could say right here is that I want I bias to be greater than or equal to 10 times my base current there. And those are the main things. And so I not only want RB small, I also want beta to be large in this. And what this means is that I wanted IB to be small. And so these two together lead to that last one that I put there. And so in the end, this is what you want to design for in order to get a very stable design point. So as you're designing, you're going to be checking these things. You're going to be checking what's my VBB, what's my I bias versus my base current. Okay, there's a question in the chat. Why do we need a large RB to get the needed IB? Simply because if you want your voltage VBB to be larger than VBE, then you need a large VCC. And you're going to be dropping that VCC across that RB, so the RB has to be big to get a base current that's going to be in the microampere range. And if you want milliamperes flowing through your device, then in general your base current is going to be in the microampere range, tens of microamperes. And if you have a voltage VCC that's on the order of 12 volts or some large voltage there, and then you need a large resistance to get that current to be very small. Okay, and so, you know, resistance is I guess off chip you don't care that much about resistance size, but when you go on chip you're going to care a lot because resistance takes a lot of space, and space means money when you're on chip. Okay, so this is the basic thing that you want here for bias stability, and I guess, you know, as design criteria, what this leads to, but doesn't say necessarily you have to do this. What I'm about to write, just understand, these are just general rules, that they're sort of starting points, but they're not ending points. So when you design your circuits later on, start with what I'm about to write, but don't end with it, because probably you end with it, it's not going to be good enough to hit your design. But let me just write here that for practical amplifier requirements, we compromise on these different requirements that we have here, and we start with this. We say, let's make our VBB about equal to 1/3 VCC. Let's make our VCE, so the drop across the collector emitter voltage, also about equal to 1/3 VCC. Let's make the voltage drop across RC, the RC resistor, which is going to be equal to the collector current times that RC value. Let's make that about equal to 1/3 VCC. And let's choose our bias current such that it is greater than 0.1 times our emitter current, but less than our emitter current. Okay, and so this here is a good starting point. Which you need, just because designing a circuit is like writing something. You know, you get writer's block. You might get circuit block when you're designing a circuit. And basically, starting is the most important thing. You've got to start, put down some guesses, see what you get, and then iterate to get to your final design. Okay, so it's a good starting point, but let's say, but not rules. Okay, you must adjust for a given design goal, especially if it's a difficult design goal and you know you're taking a class, so your design goals generally will be fairly difficult, I would say. Okay, so that's bipolar biasing. And again, the game here, just a reminder, is to get a certain collector current out of this. And so with bipolar biasing, I guess it was, you know, it looked like I went through a lot, but it actually was made very easy because we could say our VBE was equal to 0.7 volts throughout this whole thing. And I sort of showed you examples last time how we did something like that. But for MOS biasing, it's a bit different. And so I guess what I'm going to do is steal something here just to start this off for you. I want to steal this, which kind of illustrates the difference between MOS biasing and bipolar biasing. So I'll steal that and I'll stick that right here. Okay, in MOS biasing, we can use a similar biasing strategy for discrete MOS circuits. Okay, and so similar to what I'm showing on the left here for a bipolar transistor, I just replaced the bipolar transistor with an MOS transistor. The difference, though, is that you can't just assume that you have a constant VGS on. Looks like some of my stuff didn't copy right, so there. You can't just assume that that equals a constant. So that makes things more difficult because that means you have to determine VGS every time. And the reason is because the current for an MOS transistor, remember what it depends? It depends on VGS minus VTN squared. And that doesn't go up fast enough that we can say that we always have the same voltage. So just compare and contrast bipolar and MOS. So remember the bipolar curve? It did this. So it came up and then it went up and shot up with an almost infinite slope right here. So that if I had an IC prime and an IC double prime, well, even though they're different currents, they pretty much have the same VBE. There's a tiny difference between the VBEs they need. For the MOS case, it's not the same. This is going up much more slowly so that it's possible that I could have one value of IDS, that'll have a certain value of VGS minus VTN, but another value is going to have a different value of VGS minus VTN, and the difference between them is not necessarily negligible. Sometimes it will be, sometimes it won't, but in most cases, you're going to have to take a step back and say, wait a minute, I need to actually determine this VGS minus VTN. And that's going to make biasing of MOS transistors a little bit more painful than biasing of bipolar transistors. But we're out of time, so I'm going to attack this in the next lecture. So I'll see you on Wednesday.